Okay, so I pass the time to you. Thank you very much.
Thank you. It was a nice pronunciation. So, hello everyone. Today I will be talking about our paper, FaME-ML, fast multirate encoding for HTTP adaptive streaming using machine learning. Okay, so the agenda will look like, I will first start with the introduction about the topics we covered in this paper, and then I will talk about our method FaME-ML, and then follow it up with our experimental results, and then conclude the presentation. So when we check it, I think Wagner also talked about how popular video streaming is. When we look at the reports, currently 82% of the whole internet consists of video content. And we see an increase in the content resolution in the internet, especially the HD and UHD content are really getting popular. And as of now, 1 million minutes of video being streamed every single second. And these are the numbers from the Cisco forecast highlights from 2021. And the most popular approach to stream the content right now is the HTTP adaptive streaming. Here, let's say we want to watch a video and then client wants to watch this video. It goes and asks the server about the content, and then first thing the server does is it sends a manifest file for that video, which includes all the available representations and quality levels that server has for that video. And then client reads that manifest file and checks its network condition to choose the best possible quality level given its network condition. And then goes and asks for a single segment, which is usually 4 to 6 seconds of that video in that quality level. In that scenario, it says, okay, 3500 kilobit per second is suitable for our network condition, and it asks for the first segment of the video from the server. Then when the video is transmitted to the client, it consumes the content and plays it, and then asks for the next segment. This cycle continues, and until there is some problem in the network. Let's see in that step, we have a problem in our network, and the client thinks that, okay, my network condition will not be suitable for requesting the same bit width. So it checks the manifest file again and asks for a most suitable representation given its current condition. And then this time it asks for a lower bitrate and then takes the segment and then consumes and plays it. Here it continues like this. The one challenging thing here is just we need to store all these representations in the server for the same video. Like in this scenario, this is called multirate encoding. We have a single source video, and then from that video, we need to extract multiple bitrate representations, and which is a challenging process because we need to encode the same video 4 times in that scenario for every single possible representation. And here, one thing can be doing in multirate encoding is tries to address this complexity and tries to reduce the time complexity for this by using some reference representations. Let's say we can choose this one, the highest bitrate representation is the reference, and use that information while we obtain encoding this one to speed up the remaining representations. And while encoding, we have this another challenging step in the video encoding part, which is called block partitioning. And let's say we want to encode this video, and at some point in our video encoding pipeline, we need to do block matching. For that, we cannot just match the whole frames. So we need to divide the frames into smaller sizes so that the block matching can be precise. By default, HEVC does this block matching to 64 by 64 and then starts block partitioning process to determine the best possible block size for the given area. Here, the important point is if there is a high motion area, it needs to get smaller block sizes so that it can do more precise block matching. And for that process to determine the best possible block partitioning, we do something called rate distortion optimization. We have this rate distortion curve for a given CTU. Let's say for this one, we have this one initial situations. And then HEVC says, let's split one more time. And then we see that we move upwards towards right in the rate distortion curve. So this looks like a good decision. And then another decision, it says, okay, we split this one. But this time we performed bad in the rate distortion curve. So we fall back from this decision and then try another approaches. This continues like this until the best possible partitioning scheme is determined for every single CTU. Here, the problem is HEVC uses a brute force approach, meaning that it tries every single possible combination for a given block size, and which is around more than 80,000 decisions per block. And we have lots of blocks in the frame. So this is really time consuming process. And there are some approaches that can reduce this one. For example, CTU search window bound application is common in multirate encoding. Here, it's based on the finding that CTUs tend to get higher depth levels as the quality level goes up. And here, quantization parameter determines the depth level in this decision, sorry, quality level. The lower the quantization parameter is, the better the visual quality we have. So here, let's assume we want to encode the CTU. If we use the lower bound, we check the corresponding CTU in the lower quality level, check its depth level, and then limit the depth levels by using that one. So we assume that if the lowest quality has depth level 2, we shouldn't go below depth level 2. So we eliminate depth searches for 0 and 1. And we also check the upper one. Here it's depth 3, so there is no bounding applied here. So we search for only 2 and 3. In this scenario, we again search for this one. We compare it, we see that's depth 1, so we don't need to search depth 0. And here we have depth 2, so we don't need to search depth 3. This part called upper bounding and this part called lower bounding. We have the problem in the multirate encoding is we have some existing method that can speed up the multirate encoding time, but they usually use the highest quality representation as the reference. So when we do that, we cannot actually reduce the parallel encoding time because if we use the information from this highest time complexity to encode the remaining representations, and when we want to do them in parallel, we are actually bounded by the time complexity of this highest quality because we cannot fully encode the remaining representations unless we complete this encoding. So actually we have this bottleneck scenario in this case. And this is the problem that we want to address in our work. So here we use the lowest quality representation as the reference because we want to reduce these complexities to a bit lower level so that we can improve actually parallel encoding time. And we are utilizing from the machine learning part for better performance. So this, I will talk about our methods now, which is FaME-ML. So we use some encoding features to feed our machine learning model. And we first use the RD cost, which is number of bits required to encode the given coding unit size. And it's for sub-CUs, as I showed in the first one. This consists of 5 values. And we also use the variance of pixels inside the CU to give us an idea about the texture complexity. This is again also 5 values. And then we use the motion vectors. This is the average magnitude of motion vectors inside the given CTU. This also gives us an idea about the texture complexity. We use the depth level of the split decision for the given depth level. This is taken from the collocated CTU, and this is a binary value. And we have a frame level QP. And we also have the PU decision. Again, this is a binary value. So our final feature vector consists of 14 values for each CTU. And for our training data set, we use 12 test sequences defined in the HEVC common test conditions. And first, we store the YUV information for each CU. This is 64 by 64 for depth 0 and 32 by 32 for depth 1. We store them. And then we also encode the information with HEVC reference software. And we extract the encoding information that we obtained during this for the lowest quality level, QP38 in our case. These are, again, the sizes are for each CTU as are 64 by 64 for depth 0 and 32 by 32 for depth 1. And we normalize every single feature in video level individually. And then we also say the depth values are saved for remaining QPs. For reference representation, we just save the encoding information. Remaining representations, we save the depth values so that we can use them as the targets. And we divide 90% of the frames for training set and 10% of the frames for validation set. And this is an overall architecture of our convolutional neural network. We first process the YUV information here using several convolutional layers. We use more convolutional for Y channel because usually we apply some chroma subsampling in the YUV videos. So Y channels usually contain more information, so we want to better utilize that. Once we process them, we concatenate the YUV output features and then process them for additional convolutional layers and then pass them to the fully connected layers and then get a 2-dimensional output, which is the probability of non-split and non-splitting for the given YUV information only. After that, we append our feature vector to this output, intermediate output, and then final we do a final pass in the final fully connected layers and get the final decision for should we split this CPU or should we not split off the CPU. This is a binary value given by this convolutional network. And for depth one classifier, this area is removed and the remaining input sizes are halved due to reduced input sizes. So in our overall method, we first encode the lowest quality representation and save that encoding information. And we encode the other ones. I will talk about why we do this now. And then we use the information from the lowest quality and the YUV information from the raw video and then feed them to the CNNs so that we can have some decisions to speed up the highest two quality versions. Here, the reason we use CNN for only these two is just we want to focus on the parallel encoding time. So we want to have a balanced time encoding distribution between representations. And during our experiments, we found that this applying the CNN only for these two is enough so that we don't apply them for this. And we use the depth 0 and depth 1 classification for QP22 to further reduce the time complexity, but we only use depth 0 classification for QP26. And as we checked in experimental settings, we used 8 test sequences from SVT and JWT datasets. We used 5 QP levels, and we encode them with low DLP configuration of HEVC. For objective metrics, we used beyond delta rate and with PSNR and VMAF. Since VMAF is better quality with perceptual quality, we also wanted to use that. And we compared the performance with HEVC reference software and a lower bound approach. In lower bound approach, the minimum C2 depth search value is limited by the lowest quality representation. And these are the encoding results we have for individual sequences. Here we have around 41% time reduction for parallel encoding compared to the HM. And we have around 0.8 bitrate increase with bitrate PSNR and 0.3 with bitrate VMAF. The Beyond delta matrix means like we achieve the same PSNR with using how many more bitrates. So this is the value with PSNR and this is the value with VMAF. And when we check the encoding time graph, this is what we have. As we can see, purple is our method. And this is the highest time complexity encoding in our framework. So our overall parallel encoding time is bounded by this line, which is 0.59 compared to others. If we use HM, this is one value, and if we just apply lower bound, again, this is bounded by the QP22. So we actually achieve around 41% time reduction compared to the HM. To conclude my presentation, we use the machine learning-based approach for fast multirate encoding, and we focus on the parallel encoding performance. We use the lowest quality representation as the reference. And we utilize from a CNN to give a split decision for the given depth level. And this is applied only for the highest two complexity representations to eliminate the possible bottleneck encoding times without hurting the performance that much. And we achieved 41% time saving with only 0.88% bitrate increase in average. So thank you all. This is all my presentation. If you have any questions, I will be happy to answer them.
Okay, thank you very much. We have a question from our previous speaker in the panel. Okay, the first question is what was the overhead of calculating the variance during the encoding?
Okay, so for variance, this is actually calculated inside the HEVC as well. So this is not a really overhead for us. Our overhead is actually the prediction inference of the CNN, but since we do them in parallel, whenever we first encode the single CTU in the lowest quality, we can start the inference process, and this is not so complex. So we don't, overall, it doesn't actually cost us any extra time complexity using this approach. Yes, the computing overhead, as I mentioned, we don't measure that precisely as like processing complexity. We just focus on the time one. Yes, but the computing overhead is a bit much compared to the traditional one because we are using CNN. The advantage is we use GPUs, so this is actually better parallelized, but we haven't calculated the computing overhead, to be honest.
And from the previous question, it asked how do you measure the time?
Okay. Yes, I try to explain it. So in our scenario, whenever we encode a single CTU for the lowest quality version, we can use that information to give some prediction for the remaining CTUs. So when we do that in parallel, we don't need to wait for everything. So we just encode one and then use that information to feed the CNN, get the inference results. And whenever it is ready, we start encoding the highest two qualities. So overall, it doesn't cost us any overhead time-wise, but it costs us some computing overhead.
I see. Okay. And I'd like to ask about the CNN architecture.
CNN, okay, we can go back there.
So how do you arrive at this architecture?
Sorry,
So
can
I
you repeat?
understand about the why UV issues, because why usually first is bigger and also is more important, so there are more layers. And how about the others? So after you concatenate them, you still have a number of layers. So how do you decide on this one?
Our videos were 4 to 0 subsampled. So that means that we have four values for each. I mean, you get the idea, sorry, it was a bit confusing. So that's why we first apply a max pooling here for Y channel to match the sizes with the UV channels. And then we concatenate in the feature map level. Like we concatenate the feature maps, not the input sizes. And then we pass them.
Yeah. And then afterwards, you have four levels.
These are for getting more features given these concatenated feature maps. So we wanted to extend these feature maps as much as possible. And at the end, we pass them in fully connected there. So the ones that are not really useful for our case are eliminated automatically. So we just have the ones that are useful for the given decision.
We have a question from Professor Zhang. He asked, do you understand why the FaME-ML performed with at QF30? Sorry, QP30. The course is actually the frequency.
Go there. I think there was a bit confusion there.
From the result.
FaME-ML, oh, sorry. FaME-ML for this. So we didn't apply the network for these three. I mean, doesn't mean that it performs worse. I mean, it performs, yes, but this is since a machine learning, so it makes some errors. And that errors always gonna cause us some bitrate or quality. So what we saw here is, okay, the difference between this and this one is so low, I think it's like what, 0.02. So we didn't want to use FaME-ML unless it is really necessary. Because whenever we use, since it makes some errors, we have some quality degradation. So we wanted to avoid it as much as possible by getting it as balanced time graph as possible. And this was the best one we had. I'm not sure if that answered the question.
Okay. Any other questions from the audience? Okay, if not, then thank you very much for your presentation.